Hey everyone, we're continuing our series of serial bus guides today with a deep dive into the inner workings of SPI. So, without further ado, let's get into what you need to know about this serial bus. SPI, or the Serial Peripheral Interface, is another synchronous communications protocol with a long history. It was developed by Motorola in the early 80s and rapidly became a de facto standard when engineers cottoned on to the simple utility of SPI, along with its relatively high transmission rates. There's now pretty ubiquitous support in both hardware devices and software drivers. Being a de facto standard means that we can bend the rules quite a lot in order to suit what we're doing. But the flip side of that means that we need to spend some time poring over datasheets to understand each part maker's own interpretation of SPI in order to get working communications. And we'll get into that in a little while. You might hear SPI referred to as 4-wire bus, which is in part a nodding reference to I2C, which is often referred to as 2-wire bus. And of course then there's the 1-wire bus developed by Dallas Semiconductor. But it's also because in a basic setup, we need 4 wires. SPI is designed as a point-to-point protocol using a master-slave dynamic. And as you can see, each of our lines is unidirectional, but this gives us full duplex synchronous communication. At the top of our diagram, we have the chip select or slave select line. You may also see this line labelled as sync or enable on some devices. The bar over the top of the line's name tells us this is an active low signal, so it will be high when the line is idling. The next line is the serial clock supplied by the master to synchronize the transfers between devices. Then we have serial data in and serial data out. You'll find that there are quite a few devices that are labelled with this notation, but this can cause a little confusion, because on the master side, it will be the master's serial data out line that connects to the slave's serial data in, and the master's serial data in that connects to the slave's serial data out. You know it's just asking for a miswiring. To keep things simple, and so that we can use the same label on both ends of the line, the most common convention is to use MOSI, which stands for Master Out, Slave In, and MISO, which stands for Master In, Slave Out. Now, to add a little confusion into the mix, there are some folks who don't like the terms master and slave for our device functions and propose using PICO, which stands for Peripheral In, Controller Out, and POCI for Peripheral Out, Controller In on these lines. I think it's less precise in characterising each device's functional agency and hasn't really gained that much traction industry-wide, so I'll be using the traditional nomenclature in this video, but at least you'll know what it is should you come across it. One of the reasons why SPI is so popular with chip makers is that the transmitting and receiving hardware are essentially simple shift registers that are pretty easy for them to implement in silicon. In fact, the SPI bus connects the master device shift register and the slave device shift register into one long distributed shift register. So in operation, data to be sent from the master will be loaded into its shift register ready for a write operation, while data from the slave will be loaded into its shift register for a read operation, and it's a read operation from the perspective of the master which controls the transaction. The master will assert the chip select low. There may be a waiting time specified in the slave's datasheet for how long the device needs to get itself ready for a data transfer, and it's up to the programming in the master to respect that if you're not going to get junk data. With the chip select held low, the master will start sending the clock pulses on S clock. With each successive clock pulse, the bits will shift position, one place at a time in the shift register. This will keep happening until all the bits from the slave shift register are in the master shift register, and all the bits originally in the master shift register are in the slave shift register. At this point the clock can be stopped, chip select deasserted, and that gives us a moment to unload the register into our device logic. Now, the astute among you will have noticed that our bit shifting operations have reversed the bit order of our data. That's because our master is sending data most significant bit first, while our slave sends data least significant bit first, forming something of a circular buffer. While it's most common for masters to transmit MSB first, you will find a significant number of slaves that will transmit LSB first. This is another instance where you need to consult the datasheet and make sure your software handles the data accordingly. Something else that can seem a little confusing at first is what's known as the clock modes. These define how data bits are clocked through the shift register. To demystify the idea of clock modes, let's start with the basic proposition that when the clock line is idle, it can be either high or low. If we start with a clock that begins low, this is referred to as having a clock polarity or CPOL of 0. SPI uses the rising and falling edges of clock pulses to take actions. One way to do this would be to shift a bit from one position to the next on the falling edge and then to sample that bit to register its value on the rising edge. This is referred to as clock phase or CPHA 0, and this mode of operation is known as mode 0. If we again start with the clock low, CPOL 0, the other way we can operate is to shift the bit on the rising edge and then sample it on the clock's falling edge. This is clock phase 1, and this mode of operation is mode 1. But the clock can also start from high, and this would be clock polarity 1. Again, there are two ways we can operate against this clock. We can shift on the falling edge and sample on the rising edge. This again is clock phase 0 and the mode of operation is mode 2. Finally, we can shift on the rising edge and sample on the falling edge, which is clock phase 1, and the mode of operation is mode 3. And it's probably worth noting that master devices will generally support all clock modes, but slave devices tend to only support one or two modes. I keep talking about checking the datasheet for this kind of information, so let's do that with a very popular device that I have a datasheet for, and that's the Bosch BME280, the temperature, pressure and humidity sensor. When we look at our memory map, we have a register set that's kind of what we might expect. At the top, we have the least significant byte of humidity data, and under that we have the most significant byte, giving us a 16-bit value for humidity. Moving down, we have this XLSB nibble, which appears to be all set to zeros. We have the lower byte and the upper byte of our temperature data to give us a grand total of a 20-bit value. And the pressure also has a 20-bit unsigned integer value, and we find that information out elsewhere in the datasheet. Looking here, you can see that each byte has its own associated address, and you can see that these yellow bytes are all read-only. So when we want some data from the device, we provide the address and read the contents of that address. And we can find elsewhere in the datasheet that we would normally do that as a burst read, and that's a burst read of all of these registers, as it's much faster to do that than to do individual address reads. So we're reading all of these addresses at once. This also prevents us getting inconsistent data, as data measurements in the device aren't synchronized with the readouts. And I guess we're probably getting deeper than we need to here. Anyway, below the data registers we also have some configuration registers, including an option for 3-wire SPI, which we'll talk about more in a moment. We also have some measurement control registers and these calibration registers. Now we need these calibration registers because each of the measurement elements in the device have their own characteristics when they're made. So during manufacture, Bosch will calibrate these elements against standard measurements and write the calibration offsets and what have you into these registers. So when the uncompensated values for humidity, temperature and pressure are read from these yellow registers, the actual values have to be calculated using these stored parameters. Right, with that register information under our belt, when we move down a few pages to the SPI interface, what we find should all make a bit more sense. And here we are, and out of the gate we have some useful information, telling us that the BME280 supports clock modes 0 and 3. So we need to take that into account in our microcontroller programming when we want to use this device. Scrolling down a bit further, we have a timing diagram that defines how we read and write the BME280 registers. So, taking a closer look at the diagram, a transaction begins when the chip select line goes low and the master starts supplying the clock. In this case, the clock has started high, so we're using clock mode 3, which means we're shifting bits on the falling clock edge. The first thing the BME280 is expecting on the serial data in line, which is the SDI line, is a read-write bit to indicate the direction the data is going to flow. Then we get a 7-bit address, which corresponds to the register address that we want to read from or write to. Once that address is received, we're either going to continue sending another 8 bits of data for the selected register address, or if the read-write bit is a 1, then we expect to receive 8 bits of data from our device, the contents of the addressed register. If we go down the page a little further, we get an example of an SPI write, and looking at it we see that when CSB goes low, our read-write bit is sent as a 0, and that's followed by our target register address. That's followed by the 8 bits of data being written into that register. Now we're sending a 16-bit word, so we need to continue with a 0 again for the read-write bit and an incremented address where we send the 8 bits of data. This transaction completes with the chip select going back to high. And there's also an example of a read operation, which is very similar to the write. The thing to note here is we only need to supply the lower address to get 2 bytes of data back, as the register address is automatically incremented in this operation. Essentially, you just need to keep reading until you get all the data you expect to get. Okay then, that's how we connect up a single device to a master. But, realistically, most systems are going to have more than one slave device. How do we connect them all to our master? Well, part of why SPI is so popular is that it's really easy. We just connect each of the data lines together onto the same line, and all the slave devices will share the same clock line. Any number of slaves can be present, but as the number increases, there are a couple of things that we need to take into account. First of all, each slave device will need its own chip select line from the master device, and of course these can add up pretty quickly. If the pins you're using for chip select default to an undefined state on the master, you'll want to put pull-up resistors on these lines, as this should stop any uninitialized slaves from responding to transmissions before they have a chance to be properly initialized by the software running on the master. Also, if you do have a lot of slaves, track capacitance may start to become an issue, so you may have to slightly increase the clock period to compensate. Finally, as the meso line can be driven from a number of slave devices, these pins on the slave devices will need to be tri-state buffered, so that they're high impedance when the device is not selected. Now, most SPI devices do have tri-state meso pins, but as usual, you'll need to check the datasheet. If you find the device you want to use doesn't have tri-stated outputs, you could add a tri-state buffer chip that you control using the chip select line. One other thing you can do to reduce your pin usage from the master, assuming you have more than 3 slave devices, is to use a decoder chip like the LS138. This is a 3 to 8 line decoder. These are nice because they have a negligible delay, and simply by supplying a 3-bit binary value, we can select which of the output lines will be low at any given time, as you can see from the truth table. That allows us to control 8 devices from 3 lines. Although the parallel configuration is by far the most common, there is another connection scheme you may see out there in the wild, where the slave devices are daisy-chained. This only works if all the devices have an operating mode that supports daisy chaining, but assuming they do, the output of the first slave in the chain is connected to the input of the next, and so on down to the last one, which will connect its output back to the master. Data from the master is shifted sequentially through all the slave devices. The whole chain acts as an extra large shift register, with the data shifting through each device until the chip select line, which is just one line connected to all of the devices, goes high. This single chip select line makes wiring a lot simpler. This method can be used to send data to a bank of outputs or collect it from a bank of inputs. It also gives the master some feedback into whether all the devices are working correctly, as the data will pass through all the slaves before returning to the master. Right, I suppose the last configuration I want to think about is one we mentioned earlier, and that's the 3-wire configuration. Where our usual SPI configuration is full duplex using 4 wires, some devices like our BME280 can support a half duplex setup where only a single data line is used. In a typical scenario for this setup, the master will transmit a standard length command over the SDIO line. If this is a write, with the read-write bit set to 0, then the master will continue to send a fixed length amount of data. If it's a read, then the slave will use the SDIO line to send a fixed length amount of data back to the master. To finish up, we'll consider some of the pros and cons of using SPI in your project. First off, it's pretty fast. For an antique, S-clock is usually taken from a clock divider that divides the microcontroller's system clock by whatever amount the user sets in the divider's control register. The minimum divisor is usually 2, so you could drive S-clock at half your system clock rate. But of course you'd need to check your slave device's datasheet for their maximum rates, which will probably be slower. Most of the time you're looking at clock rates between 10 and 25 MHz. As the transmitter and receiver both use the same clock, neither the master or the slave need a precision oscillator. So the clock period, phase and duty cycle can vary quite a lot, but it's all good as long as the minimum clock period requirement is met. The push-pull drivers on the signal lines make for good signal integrity. Data size isn't limited to just 8 bits. In fact, the message size, its content and purpose are all pretty arbitrary. As SPI is a point-to-point protocol, there's no device address requirements, which means both our hardware design and software are pretty simple. On the flip side, SPI doesn't easily give itself over to bus sharing. It's set up for a single master, and the more slaves you have, the more pins you'll need on your master to control those chip selects. If your slave device needs to use interrupts, you'll need an extra out-of-band line for that, or you'll have to periodically poll the device. Finally, you need to remember that the master generally has no idea what's going on with the data being transferred. There's no flow control or acknowledgement, and there's no error checking protocol. So if the slave is not working, or did not understand the control byte, or has any other problems, the master is going to receive garbage data and will need to determine this itself from what it receives. This is perhaps not ideal in critical systems. And that concludes our short tour of SPI.
Well, that's it for today's video. Thanks for watching, and all that's left is to say stay safe and see you soon.